All right, everybody. Um, as I was thinking about what we might talk about today, I understand that your focus is on an exam. And so I don't want to stand up here like Santa Claus at the North Pole and tell you we've had another very successful Christmas and now it's time to start preparation for next Christmas, because I'm dumping new reactions on you in preparation for exam 3, which you're not even thinking about yet. So I'm going to keep the new material a little bit light today and instead tell you a story of how the kinds of reactions we've been learning about change the world. And the story actually starts in the ancient world with how we used to get color in clothing. It used to be there weren't that many ways to get colorful clothing, particularly reds and purples. Here are some examples of natural sources. Oh, by the way, whenever I do this, someone inevitably raises their hand and says, "Is this important? Is this going to be on the test?" So let me just say, yes, everything I say is important. And yes, everything I say will be on the test. No, I'm just kidding about that. Your point is to not memorize molecules, but just look for chemical reactions and principles, okay? I realize that's unsettling, but come on. So here are some natural sources of color. In nature, you can get the dye indigo from this plant. A dye that shows up in Scripture is this dye called Tyrian purple, which comes from a Mediterranean sea snail. And this is actually, you can look it up in Acts chapter 16. You can read about Paul and Silas meeting Lydia, who is a seller of purple, and she became a great resource to them as they were trying to figure out where to stay, and became a faithful member of the church. But she likely had a fair amount of wealth because purple was so difficult to get your hand on. Imagine if you have to go fishing or diving for sea snails and then have to bring them up and grind them up and extract the dye. This is probably a whole lot of work for a whole little bit of dye, and only the very elite could afford it, and that's why purple is the color of kings and emperors. It was so expensive. And there are other natural sources of dyes, but basically this was pretty difficult to get, and so clothing was mostly plain unless you had a lot of money. And this was true even until the mid-1800s. Excuse me. So a man named William Henry Perkins was 18 years old, and he was working in a lab, and he was interested in making the anti-malarial drug quinine, which could be isolated from a natural source, but he thought, why can't we just make this synthetically? And there wasn't a lot known back then. There were new chemical techniques. You could basically figure out the relative amounts of atoms in compounds, carbon and nitrogen and oxygen and so on, but connectivity was not known that well. And so I could show you the structure of quinine, but basically Perkins thought, I always get confused. It's not Perkins. His last name is Perkin, whatever. Anyway, this guy thought that he sort of figured out that if he combined a couple of these different molecules together, he would sort of have the molecular formula for quinine, and so thought, why not? Let me just mix them together and see what happens. And, he was 18, so probably he was a little bit overly optimistic about his own abilities. So he mixes this molecule, aniline, which he figured out, if I have 3 of these, that I bring them together, I could make quinine. And his aniline sample had a couple of impurities in it. So this is a benzene ring with a nitrogen. That's called an aniline. You don't need to worry about these names, but this is called toluidine. It's like toluene, except it has a nitrogen. This is the ortho. This is the para-isomer. And then he used oxidation conditions. Maybe you remember that from 351, potassium dichromate and sulfuric acid. You use that to oxidize alcohols to carboxylic acids, or at least primary alcohols and secondary alcohols to ketones. And I'm not sure why he chose this, but and I think he was doing this in his house. So I don't know what 18-year-old decides he's going to do chemistry. Actually, shoot, my son Nate, who's a freshman here, he's actually going to be in that room, W2022 next hour, so maybe I'll have him come in. He used to have a lab of sorts in our garage where he was trying to smelt metal, and it was always kind of interesting. He ended up doing his part to fight inflation by melting down and extracting the zinc from some pennies. So he's still got these zinc ingots, but we never got his forge hot enough to melt other interesting things. Anyway, so he's overly optimistic. He puts these things together, and he ends up with a disaster, which is when everything in the reaction mixture sort of falls out and forms black chunks of who knows what at the bottom of the flask. So, and this happens sometimes in the lab, and so you set to work cleaning your glassware because you need to use it again. And, normally, or if you have a lot of resources, you just throw it away and start all over. And a lot of this stuff, the tarry, gooey mixture, you have to scrape out with a spatula. It's pretty tough. And he was washing this flask with this black solid with alcohol, probably with ethanol, and it was purple. The ethanol that came off this black solid was purple. And he thought, oh, wow, that could be useful. And so he isolated it. And or he continued to extract it and concentrated it, and it was a very, very bright purple dye. He patented it. He's 19 now. He opens a factory in England in 1857 to manufacture this dye, not even knowing what the structure is. He called this dye, I don't know how to pronounce it, mauvine, because it was sort of purple, like the color mauve. I don't know. How do you say that? Mauve, is that right? That's the color-ish? Who knows? He retired at a wealthy man at age 36. Okay, I am 42, so I'm way behind that. And spent the rest of his life doing self-funded chemical projects. And to this day, he's respected. One of the top medals awards you can get from the American Chemical Society is named after Perkin. But that's not all there is to it. This is not just a story of making purple clothing and making one young man fabulously and serendipitously wealthy. But this sparked a whole bunch of research into other dyes and actually contributed to the chemical industry into generating antibacterial and anti-cancer drugs. So it was the start of sort of a revolution in chemistry. This is, by the way, an actual sample of his mauvine. Still exists in the bottle. It's still purple. I don't know who has that, but it's something by William Perkin, 1856. So, and this is, I think, an actual cloth that was dyed with his particular dye. So suddenly, purple became accessible to the masses. So if you're wearing purple, or really any color, you can trace it back to the revolution in the textile industry that occurred when dyes became available. So much later on, after people were using this, chemists developed analytical techniques that let them discover the structure. This often happens in science. You find something that's useful and you use it without knowing what it is or how it works. And then more insight comes later. So this is the chemical structure of mauvine A. It's actually a mixture of compounds, but this is one of the major ones. And these were the starting materials, as I said, aniline, and then these ortho and para methyl anilines. And you can sort of see in the mauvine product the individual aromatic ring subunits. You can see where they came from. So the orange portion here probably came from aniline, and this one did too. This portion here with the ortho nitrogen and ortho amino and methyl groups probably came from the ortho aniline, and then in green is the portion that came from the para-aniline. Now, I'm going to show you what chemists think happened to make this molecule. In red are the connections that were made between each of these subunits. And the reason I'm going to do this is because it involves the mechanism of electrophilic aromatic substitution, which we've spent the last couple of lectures on. Don't worry about anything here that's not electrophilic aromatic substitution. I'm going to try to show you at the beginning how an electrophile was generated. So this is a proposed mechanism. If you start with the para-toluidine, the para-methyl aniline, presumably potassium dichromate can remove a single electron from that. How that mechanism occurs is not, I don't understand, but there's a precedent in nature for single electron transfer reactions. You have a metal that's that wants an electron enough, and it can just steal one from the pi system. And so you end up making a radical cation, which can then be oxidized again to form this imine-like structure. And so this, you could think of this structure as being sort of an extended carbonyl, right? It's like you've got the imine here, it's conjugated and conjugated there as well. So you would expect this to be electrophilic, at the carbonyl carbon, and then at the beta carbon, and then at the, I guess, delta carbon, if you want to think about the chemistry that way. Moreover, if a nucleophile attacked here, I'm getting it wrong. I guess the nucleophile attacks at the nitrogen. In any case, the thing that's driving this forward is that as the nucleophile attacks, you restore aromaticity to the ring. These electrons kick down here, these go here, and these go somewhere else. And so here's an example of that reaction happening. Again, don't worry about the details of this electrophile or why the nucleophile can attack here, but just observe observe the electrophilic aromatic substitution reaction. Electrons from the pi bond attack the electrophile. We get an intermediate, a carbocationic intermediate, and frankly, we don't need these arrows at all because we could simply draw the structure like this, and then a base removes the proton, reestablishes aromaticity, and you've made your connection between one of the aniline units, and what was your electrophile. Okay, so again, please do not worry about this or why this molecule is electrophilic at the nitrogen. You can accept that on faith, but the idea that you could generate this connection via an electrophilic aromatic substitution reaction is important. All right, so the success of Mavine A and the fabulous wealth of young Mr. Perkin, I actually don't know whether he got his PhD or not. This is like a total rags to riches kind of story. It's a good thing social media wasn't a thing back then, right? Because he'd have been all over and been an influencer of some sort. Anyway, I don't know what you people call them. I understand Facebook, but I really don't understand Instagram that well. But you guys are actually beyond Instagram too, right? It's something else now. I don't know. I told you I'm 42. Okay, so a lot of other research was done to generate other dye molecules, right? If you observe it can be done by somebody, then all of a sudden all the scientists and innovators are thinking, well, we can do it cheaper and better. And so a new class of compounds were discovered, and these are called azo compounds. They are characterized by this nitrogen-nitrogen double bond, and then each of those nitrogens is itself attached to a benzene ring of some kind, an aromatic ring. These are highly conjugated, and as you maybe learned in the chapter on conjugation, the more highly conjugated a molecule is, the smaller the gap between HOMO and LUMO, and that eventually gets to the point where the photons that can promote an electron from HOMO to LUMO have wavelengths in the visible region. And so then you start getting molecules that absorb some visible light and reflect the other wavelengths of light, and this is where we get color from. So many of these molecules are highly colorful. Here are a couple of examples. You may have heard of Congo red as a dye before, but you can see the basic idea. You're using this linkage between nitrogens to make an extended conjugated system between aromatic rings, and then you can continue to elongate it, and there's all kinds of stuff that you've learned that you can do easily to aromatic rings to see how it affects the dye, right? So, for example, you can see that the simplest aromatic azo compound probably would have been just the benzene ring version. And I don't actually know whether that was colorful or not. But you can see how people could very easily say, hey, why don't we try naphthalene instead of benzene? Let's put another aromatic ring on that. Or why don't we try adding a nitro group? We know how to do that through the nitration reaction. Or why don't we try the sulfonation reaction to put the sulfate group on the aromatic ring? And this idea of varying the structure, the core structure of a molecule to see what the effects are is essential to basically all chemical research. This idea that the structure of the molecule is related to its function, and that by perturbing the structure, you may discover new functions. So this is kind of the structure function principle allows you to explore and optimize molecules and discover new functions just by making variations in structure. And sometimes you don't have any rhyme or reason for doing it other than, let's see what happens when we do this. So at about this time, as these dyes were being developed, a German chemist named Paul Ehrlich was getting his medical degree, and he was studying, he was working on techniques for staining bacteria and histological samples with dyes. If you've ever looked at cells under a microscope, they look transparent and it's hard to see them. So sometimes you stain them so you can detect the subcellular structures like the mitochondria or the nucleus or the ER. So he was interested in developing dyes that do this. And there's tons of these today. There's a whole field of histochemistry and immunohistochemistry, but he was just taking the available dyes and saying, okay, let's see what happens when we stain samples with dyes. And he noticed that there was one particular sample of a dye called methylene blue. You still may encounter this in the lab as an acid-base indicator. There's a chance in 107 that you had some dealings with methylene blue. Shoot, I'm remembering when I was a freshman here, I lived in Deseret Towers, which is now gone. So that tells you a long time ago. And there got to be a point in the year when people started playing pranks on each other. And there was this guy and this girl in my ward that kind of liked each other, and they decided to demonstrate this by, I think he made her a bunch of brownies that were soaked in methylene blue so that she would pee blue and be shocked and appalled. Anyway, I don't recommend doing this. Please don't do it. But suddenly I was remembering where I had encountered methylene blue before. I was not a party to this. At best, I'm an accessory after the fact. Yeah. Are there medical effects? There are side effects to methylene blue. I don't know what they are. How dangerous? The question is, how dangerous is this? And my answer is extremely. Don't do it. Okay. So he noticed that this dye, methylene blue, stained a particular parasite, Plasmodium, that's responsible for malaria. And he had a grew light bulb moment where he thought, if the dye stains the Plasmodium parasite, that means the molecule is getting inside the cell. If it's getting inside the cell, couldn't I use it to kill the cell? And so he gave it a try. And it actually worked. Like, they gave this methylene blue to some patients that had malaria, and they got better. So the idea of chemotherapy, or rather a molecule that can treat a specific disease, was born. And this was in the late 1800s. Now, methylene blue had some side effects, which I'm not aware of, and that's why I'm saying it's dangerous. Don't do it. By saying that you agree to release and indemnify me in perpetuity from all liability associated with your own poor choices for methylene blue, you have been warned. Okay. Just got to make sure that's on the record. He continued to look for other molecules that could have specific targeted effects and that could kill other kinds of pathogens, and stumbled upon this azo dye that's called trypan red. And this kills trypanosome, which is a sort of a tropical parasite. And again, you see it's a red molecule, highly conjugated, but it gets into cells and kills them. Now, I don't know the mechanism for that. And actually, in modern medicinal chemistry, it works best when you understand the mechanism of disease and develop a molecule that targets a specific part of that disease. But at this stage, they were throwing molecules at cells and seeing what happened, and it worked. Later, they developed this molecule called arsphenamine. This is an arsenic derivative. So if you look at the periodic table, arsenic is a couple rows down from nitrogen. So they're putting arsenic in the place of nitrogen, but it's still sort of like an azo compound. This the structure actually is probably more complicated than this, but they discovered that this killed the bacteria that causes syphilis, and this was around 1909, and suddenly this became the most widely prescribed drug in the world. Which suggests that some of the Victorian sensibilities about sexuality were disconnected with people's actual behavior because it was prescribed so widely. But anyway, this idea of rapidly screening compounds to see what they do and targeting specific pathogens and being able to vary the structure to get a desired outcome is an important is the foundation for basically all modern pharmaceutical research. For this, Ehrlich won the Nobel Prize in Physiology or Medicine for this idea of chemotherapy, and to this day, the idea of a magic bullet drug that targets a specific thing and does a specific outcome without side effects comes from Paul Ehrlich's work. And if you want to read more about that, there's a book called The Emperor of All Maladies by Siddhartha Mukherjee, and he takes you through the history of cancer from thousands of years ago through sort of modern cancer research. It's quite interesting, and this is an important part of the story. Anyway, do you have questions? I'm sure I don't have answers on this, but anything you want to know? Sure, yeah. In the structure for methylene blue, it looks like there's some Texas carbons. Is that right? I was in a hurry when I drew that. Thank you. You are absolutely right. There are Texas carbons there. And So thank you for that. I apologize. I'm humbled. Oh, by the way, is that aromatic? You better be able to figure that out. Actually, there's nothing so complicated on your exam. I've already written it. But you say yes. Which lone pairs count? Not those, and not those, because each of those atoms is already involved in a pi bond. So you got 2, 4, 6, 8, 10, 12, 14. We hit one of the magic numbers for aromaticity. That means we fill the lowest energy orbital and all the pairs of degenerate bonding orbitals without populating anti-bonding orbitals and without having half-filled orbitals. Okay, thank you for pointing out the Texas carbon. Other questions? Okay. So what I will show you some today is how you make a diazo compound. And these are going to be useful, or how you make one of these azo compounds. So we've already learned that you can take a benzene ring, you can, via the nitration reaction, install the NO2 group, and then you can reduce that NO2 group to the aniline. All right. Or if you want, you can just buy aniline, but if you're on an exam and need to do it starting with benzene, that's how we would do it. Now, how do we get from having one nitrogen to having two nitrogens double bonded together and another aromatic ring on the other side? This is going to involve a process that is known as Diazotization, which isn't worth knowing. I mean, isn't worth memorizing that term, but that may be how we describe it. And that involves treating the aniline with nitrous acid. So you actually use sodium nitrite in HCl and water, and what that does is it converts the aniline into the following functional group. This is called a diazonium ion. Okay? So that's crazy. That looks like make 'em up sort of Lego chemistry. How did that happen? It's actually not as bad as you think. If you draw, a nitrous acid is not particularly stable. If you draw the Lewis structure of the NO2 minus anion, it looks like this. And in the presence of acid, of HCl, you can protonate that negatively charged oxygen to get HNO2. And actually, you can further protonate that oxygen to have H2NO2+. At that stage, you sort of have a good leaving group on the nitrogen, and so lone pair electrons on the nearby oxygen can kick down, sort of in carbonyl chemistry format, to kick off the leaving group, and that generates the following cation, which has a resonance structure like this. And this is called the nitrosonium ion. And this is a good electrophile. So what happens next is that the lone pairs on the aniline nitrogen will attack the nitrosonium ion. I'm going to use this particular resonance structure. And that positive charge on the nitrogen represents probably an empty p orbital on that nitrogen in the way we're drawing it here. And so the lone pairs attack that orbital, and we get as a product or as an intermediate, oops, no, that's right, isn't it? Okay, and then we can have some base, perhaps the conjugate base of our acid, remove this proton, and that gives us what's called a nitrosamine. So we've established there the single bond between the two nitrogens. At this point, getting from here to here is just a matter of proton transfers and losing water. So let me try to show you this in as simple a way as I can. And I'm going to condense some proton transfer steps into the same step so you can get an idea of what's going on. If I remove this proton and then have these electrons kick down here and then have these electrons from the nitrogen-oxygen pi bond pick up a proton from some acid, I establish the nitrogen-nitrogen pi bond. Okay. I mean, maybe I rotated it, so I know that's probably disturbing. Okay, and then if I have, let's see, if I have the lone pair electrons on the oxygen pick up a proton from some acid, that will become water, a good leaving group, and then these lone pairs on nitrogen can kick down and the water can leave. And that will get me to my diazonium product. Okay. So I've shown you that mechanism because I learned about this reaction when I was taking 352 and I promptly forgot it, and it came back to bite me on an exam. And I felt like I didn't understand the mechanism, so when I see mechanism, that helps me remember what happens. I'm not going to test you on this mechanism, so don't worry about it. But you should know how to use this reaction in a synthesis, how to predict products, and how to provide reagents. Okay, questions about that? So you can do this with alkyl amines as well, but alkyl diazonium salts are not stable. They rapidly degrade because, imagine this. This is, man, where's that sidebar thing? Sorry, I'm trying to, oh, there it is. Sorry. This is an excellent leaving group, right? It could leave as nitrogen, and once it's gone, it's gone. And so what happens with alkyl diazoniums is the resulting carbocation is stable enough that it's reasonable to propose that this happens. And that little arrow there just means that nitrogen gas bubbles off. In contrast, if nitrogen were removed directly here, that positive charge would sort of, instead of being in an empty p orbital, that positive charge would sort of be on an sp2 hybridized carbon in an sp2 orbital, and that's highly unfavorable because orbitals with s character are close to the nucleus, and you don't want positive charge to be close to the nucleus. In any case, so the alkyl versions of this are not stable and not useful. I will just say, because your text points it out, that this nitrosamine intermediate sometimes can be formed in food products and can be associated with potential negative effects in carcinogenesis. At some point, people talk about nitrites in hot dogs, and nitrite is NO2 minus, and so that likely has something to do with forming the nitrosamine. Yeah?
What's the regioselectivity of the diazonium ion?
Regioselectivity of the diazonium ion, we're going to see that the diazonium ion is not a good nucleophile. Well, we're going to use the diazonium ion in a different kind of reaction. You would predict, though, that it's an electron withdrawing group. I'm sorry, the formal charge on the diazonium ion, for those of you playing along at home, is right here. And you can draw resonance structures where you move electrons from the benzene ring out onto the nitrogen. So you would predict this would be an electron withdrawing group via resonance, and probably a meta-director. Therefore, in many cases, if we want to make a diazonium salt that has groups on it, we will put those groups on the benzene ring first and then do the diazonium synthesis. Other questions? Okay. Well, let's talk about some things you can do with this aryl diazonium. The first one gives us a chance to revisit something we sort of neglected in chapter 20. And that is the idea of doing a nucleophilic aromatic substitution with a benzene ring. Why can't we bring a nucleophile in there? So we talked before about how we didn't have a method for making phenol, about getting an OH group on a benzene ring. It turns out, because the N2 group is such a stellar leaving group, we can actually replace it with the OH group. And the mechanism goes like this. The oxygen attacks the ipsocarbon, because that's where the leaving group is, and that generates a resonance stabilized intermediate with a negative charge in the benzene ring, and you've disrupted aromaticity. Oops, sorry. It's an OH group here. Hopefully you can see how the negative charge would be delocalized on these three atoms. But you now have a negative charge adjacent to a stellar leaving group, and so you can do basically classical elimination chemistry. Electrons kick down, leaving group leaves, and you make nitrogen gas and you make your phenol. Yeah?
So why would it not just kick off the leaving group in the first place instead of disrupting aromaticity first?
Why would it not just kick off the leaving group to make this intermediate?
With the OH attacks.
Right. I'm saying, oh, okay. So you're proposing an alternative mechanism where OH attacks, SN2 format, where OH attacks and the leaving group leaves in the same step. That's essentially a geometry issue. The SN2 reaction happens as a nucleophile attacks the antibonding orbital between the carbon and the leaving group. And that antibonding orbital points 180 degrees away back into the benzene ring. So the nucleophile cannot get there because the benzene ring's in the way. So SN2 chemistry really doesn't happen on benzene rings. Instead, the mechanism is more of a carbonyl type addition in the first step and then elimination in the second step. So yeah, it's just that other alternative pathway where the oxygen would displace the nitrogen directly, that's too high in energy to work. It's a similar issue. Do you remember why you couldn't do SN2 reactions at tertiary carbons? Because the nucleophile couldn't get in close enough on the backside. It's the exact same issue here. All right, what else? So your text has a number of different reactions you can do to install other groups in place of the N2 ion. For example, if you take this same starting material and you use copper iodide, I think the copper actually is doing something there, but your text doesn't say what, and I'm not really sure, so we'll just ignore that. You can replace the N2 leaving group with iodide. That's useful because there's not a good reagent for doing electrophilic, installing an iodide on a benzene ring like we did for bromine and chlorine. There's no analogous FeI3 reaction with I2. So this is how you would get iodide on a benzene ring. There's also conditions for putting fluoride in a benzene ring, though I sort of forget what the reagent is. So stay tuned and we'll talk about that next time. But this is interesting. Some of you have asked, well, can I put fluoro on the ring? The answer is yes, but not via electrophilic aromatic substitution. F2 is just too violently reactive. You try to react that with Fe, some iron, Lewis acid in a benzene ring, and you're going to cause an explosion. So this is a better way to get fluoro on a benzene ring. But doing that is critically important. There are a lot of drugs that have fluoro groups on aromatic rings. And so this is particularly useful. So we'll go over that again next time. But I want to show you how you can take the diazonium salt and use it to make an azo compound. So to do this, you have to see that you can imagine that this compound is electrophilic on the terminal nitrogen. We've got a positive formal charge on that nitrogen, but we could draw a resonance structure in which we move these electrons down onto the first nitrogen, and then it's this one that has the positive charge. It's not so very different from, I don't know if you remember when we were doing Friedel-Crafts acylation, we had an acylium ion intermediate, which had a triple bond with oxygen, but you could draw a resonance structure that had a positive charge on the carbon. This is kind of like that. Only I guess for full analogy, we should have drawn them in the same sort of orientation. Okay, so the diazonium ion is very similar to the acylium ion. And so a nucleophile, you could draw and have, just as we had a nucleophile attack the carbonyl carbon of the acylium ion in either of these resonance structures, so we could have a nucleophile attack the nitrogen in one of these resonance structures for the diazonium ion. So if that nucleophile is another benzene ring, here's what happens. Nucleophile attacks electrophile. You get an intermediate that is no longer aromatic on this ring, in which you've made a new carbon nitrogen sigma bond. Then a base removes the proton, and you're left with your diazo compound. And now you can begin to see that if I already had functional groups on either of these benzene rings before I made the diazonium salt, I could I could have made some of those dyes that I showed you earlier on. Okay, questions? Yeah.
How come the chlorine, when you make the diazonium, doesn't like kick off that?
Yeah, so that's a great question. The question is, once we make the diazonium ion, the counter ion is Cl minus. That's stable. We don't have Cl minus come in and attack. Why not? And presumably that's why we use copper, because you can do this. You can put a chloro there using copper chloride. Somehow, I think the copper is needed to facilitate the N2 group leaving. I don't exactly know why or how, but yeah, you need it in order to get the reaction to go. Otherwise, the chloride salt is stable. Yeah. So, what else? Okay, well, you got an exam, so you better go study. Have a good weekend. I will see you next time.